Hi, good morning, everyone, and thanks for taking time to join us today. My name's Conrad, and I'll be your host for today's session. Welcome, everyone, to Ansys Lumerical for Photonic Integrated Circuit Design with Yael Olivier. She's with RAND Simulation, and she's our optical application engineer. And we also have a special guest, Guanhui Wang from Ansys, and she's on the Lumerical ACE team. So thank you all again, and thanks to our presenters. And Yael, it's all yours now.
Thank you, Conrad. So today we're going to talk about photonic integrated circuits with Lumerical Interconnect. I am Yael, as Conrad introduced me, and later on in this presentation, we're also going to hear from Guanhui Wang, and she'll be walking through the workflow. So I'm just going to go ahead and get started here. So on today's agenda, we are going to go over, of course, photonic integrated circuits, how we can leverage simulation, an introduction to the actual circuitry, an introduction to Lumerical Interconnect, which is the software that we're mostly going to be going over today. Then I'm going to, of course, pass it over to Guanhui for the workflow and walkthrough, and she's going to go through some examples and talk about the component to circuit design and how the CML Compiler and Verilog-A help during the design process. To start us off, what the heck is a photonic integrated circuit? I think before we get into the photonic integrated circuit, we should probably take a look at what is an integrated circuit. So an integrated circuit is a collection of electronic components, usually seen on chip. That's usually what we call it. So the electronic components that we'll normally see are resistors, transistors, capacitors, etc., and they're all stuffed onto this tiny little chip that we see on a circuit board. So that's that black chip that we can see in that first image there. They are all connected together to achieve a common goal. They come in all sorts of flavors, like single circuit, logic gates, op amps, voltage regulators, motor controls. This is all just electricity that we're talking about here. So what happens if you were to make it a photonic integrated circuit? So it's basically just an integrated circuit with kind of the same structure, except now we're adding photonic components. So instead of just using electricity and electrons for data transfer and communication, now we're looking at using photons as well. So instead of just using resistors, transistors, and capacitors, we're also using optical components like waveguides, fibers, and phase shifters to help transfer that light. So photonic integrated circuits, I'm going to start calling them PICs from now on. It's just going to keep it a little bit easier. So PICs use laser light similar to turning on a switch to inject electricity that drives electronic components. Now we're just doing that with photons. So this is the big play here, is the photons versus the electrons and how they're working together. So in PICs, the vast majority of communications data is channeled through the photons, while still the communication is still performed by the electrons. The communication, the logic of it is still performed by electrons, but actually transferring the data is done by the photons. So an example of the communication channel for the photons to go through is a waveguide. So waveguides are the interconnects between photonic devices in the circuit, which are usually made from a silicon core, which may look like a fiber or a rib of fibers. This kind of acts as our quote unquote wires of our light system. So kind of getting into a little bit of like the silicon photonics of it all, PICs are commonly made from silicon photonics, or the name is used interchangeably. If someone's saying silicon photonics, usually you kind of assume that they're doing something with PICs as well. Because it is, so we use the silicon photonics because it's very compatible with the CMOS fabrication, and a lot of these PICs using the silicon photonics can be manufactured within the same foundry structure as the integrated circuitry that we were talking about before. It should be mentioned though that we are still seeing indium phosphide and silicon nitride being widely used as well. I was just keeping it a little bit simple here with just talking about silicon photonics. So right now, our world is growing in data consumption. I mean, we're looking at Netflix. We're basically everything is done through the internet. Especially, I mean, I'm sure a lot of us are still working from home. This is causing a a need for more data consumption, a demand for faster networks, and as technology is still growing, we need to find more sustainable solutions, as well as just trying to keep our energy as as low as possible. So PICs offer more like a more efficient solution with the ability to make the chips even smaller, so the miniaturization of them. They provide a higher speed because we are now talking about the speed of light versus the speed of electrons. They are also a lot more efficient with thermal and power consumption when compared to electrons and electricity. They're compatible with the technology that we are currently using, which makes it a lot easier to start fabricating them, especially with the current foundries that we have for integrated circuitry. So basically, once that they are out of the research and development stage, it should allow for a high yield, high volume manufacturing at significantly lower prices. But of course, everything that's new is more expensive to begin with the design process. So the main applications where we're seeing PICs is in healthcare, transport, defense and aerospace, and mostly data communication. So in healthcare, we are seeing it with photonic biosensors. So for example, this is a real photonic biosensor chip that's pictured right there. These are photonic transducers. They basically pick up on small changes of refractive index that arise when the target molecule interacts with the coating on the sensor. And they're basically using a miniaturized version of an interferometer on the photonic, or as a photonic system on the chip, so they can have a high speed analysis of that molecule. We're seeing it in the transport area, so a lot with LiDAR in cars. Until now, the challenge of bringing LiDAR to the market has been because it's high cost, and trying to make something that's low cost, high volume, and high performance, and lightweight enough to stay with the car has been an issue, but PICs are slowly changing that. And especially with the electrification of cars, we are really seeing a pickup in the trying to make things a lot more efficient, a lot lighter, so we're using a lot less energy consumption. And when we're thinking lighter and smaller, usually PICs is where the answer is, because we wouldn't need as big of a cooling system for this for the electronic system in general. Mostly we are seeing it in data communication, so we can think of fiber communication like fiber internet, which most of us have now, and I'm sure a lot of us are enjoying. So not only can PICs increase the bandwidth and data transfer speeds, they can also, as I was speaking on before, reduce energy consumption in data centers, which is why, basically cooling down our electrical servers is a really large part of the energy makeup of keeping servers going. But utilizing light, it really does cut down on the thermal on the thermal implications of the circuits. And of course, then we are also seeing it in defense and aerospace. Of course, they don't really want to talk about it, so we do see it in monitoring systems, and basically everything that we are seeing within the healthcare, transport, and data communication is taking part in the defense and aerospace systems as well. So why leverage simulation? As you can imagine, PICs are tiny. I mean, a couple slides beforehand here, it was shown on top of a little matchstick. So it makes it pretty hard and expensive to develop and process the first iterations and to test and prototype them, because they are so small. It's not like you can just easily build one in a lab on a lab bench and kind of see what happens, right? So simulation allows for predicting more accurate testing and analyzation of the circuit performance prior to the physical testing, which allows for a lower yield rate less time on the project and allows it to be more cost efficient. So this leads us to Ansys. So in Ansys, we have a complete software system package for most physics. So we can talk about fluids, structural mechanics, electronics, semiconductors, and of course today we're going to be talking about the optical and photonics software systems. So we have an end-to-end multi-physics and optical simulation platform. What does this mean? That means we can start from the chip and build an entire, we can go from Lumerical to Spios being everything giant, everything 3D. We're putting this out in the environment, and Lumerical saying we are turning electricity into light, light back into electricity. And we're looking at the, like as small as like the CMOS sensors. So Lumerical is of course what we're going to be talking about mostly today. This is what we're using for our photonic simulation of sensors, waveguides, micro lenses, anything on a chip level or nanoscale. That is what we use Lumerical for. Then in the middle there we have ZMAX, which is mostly for modeling macroscopic optical components with a lens stack. And this is where we would optimize your lens system. If you're trying to make a camera, a projection system, this is where you would kind of, this is your tool, right? So for Spios, we have also, it's still optical component modeling, sort of, but if you can imagine ZMAX being more for the optimization and as if you were to be working in a black lab, everything dark, temperature controlled. Spios is we're going to take that system and put it out in the environment. We're going to see how the sunlight looks on it. We're going to see that how humans perceive the light. So it's a much more expanded version of optical system modeling. Getting into Lumerical. Lumerical has an onslaught of tools. So it really depends on your application and what you're trying to do, dependent on which tool that you would use within Lumerical. Today, we're going to focus on the first quadrant for photonic integrated circuit simulation. So that's that first top quadrant there. We're going to go over Lumerical INTERCONNECT and see how the CML Compiler and Verilog-A platforms fit into it. Onto the side of that chart, we do see that Lumerical is a great tool as well because of the interoperability capabilities. So we can use Lumerical with HPC packs. We can use it with APIs such as MATLAB, which is a big one, and it has the Ansys synergies, right? So if you needed to upload a meta lens or something into ZMAX or a diffractive grating, for example, into ZMAX, you can easily do that because of the dynamic links. If you wanted to, take it to the electrical side and use HFSS, you could do that as well. And on top of all of this, we also have the Foundry support. So if you wanted to actually get something made or need help with, creating one of these circuits, that's possible. So focusing a little bit more on Lumerical INTERCONNECT, this basically is the complete design package for making photonic integrated circuits. So in the circuit simulation, we have both frequency and time domain simulation. They both support bidirectional and multi-mode circuit topologies. We also have the built-in element library, which has all the necessary components that you would need to build one of these circuits, such as sources and analyzers. It also includes some electrical elements for active component simulations. This is kind of where the compact model library plays in, so what we call the CML. This is where the CML can be generated, published, and managed using INTERCONNECT, so you can use the simulation results to help build your CML library or experimental data. INTERCONNECT also does parameter sweeps and optimization work as well, and it's a great place to start your analysis of your circuit design. So whether you're dealing with the actual circuitry or you're trying to see, the optical transceivers, modulators, whatnot, this is where you would go. Diving a little bit deeper into the frequency and time domain simulations, the frequency domain solver calculates the response of the circuit represented by the scattering of matrices, each of them representing a frequency response of an individual element. We can also look at the analysis of the circuit behavior through amplitude, phase, group delay, and dispersion. So that is all done within the frequency domain analysis. And for the time domain simulation, INTERCONNECT uses a dynamic data flow scheduler. Basically, this allows for more flexibility than traditional discrete time or time-driven simulators. The scheduler simulates the time domain wave, from signals for each element and propagates them bidirectionally. The analysis tool makes it easy to extract eye diagrams and figures of merit, such as the bit error rate. So from here, I'm going to now pass it on to Guanhui, and she is going to walk you through some of the workflows.
Yep, thank you, Yale. So today we're going to talk about the photonic component design environment. Actually, the electronic photonic design automation workflow, the EPDA design workflow. Yeah, so this is the full workflow we jointly developed with Cadence. It is the state-of-art electronic photonic design automation workflow, and it is the solution that we use the in-class photonics and electronic tools to provide for the peak applications. So start from the top. For the photonic component designs, we've built a direct integration bridge between the Virtuoso layout suite, which is Curvy Core, and Lumerical multiphysics simulation tools to provide a seamless design environment for component layout and simulation. We also provide Lumerical Compiler Model Library Compiler, CML Compiler, as a cross-simulator photonic component model, compact model development platform. So to make, that is to take the component simulation data and generate the compact models for the photonic PDKs. And moving to the bottom, to facilitate the electronic photonic integrated circuit designs, we've integrated Lumerical's photonic circuit simulator with the Cadence Virtuoso. This design environment allows users to design hierarchical integrated circuit schematic using Virtuoso schematic editor and to perform circuit analysis through the Virtuoso ADE. From the ADE, users can perform optical time and frequency domain analysis on their photonic circuits by using INTERCONNECT as the engine. User can also perform the full system simulation on both their electronic circuits and photonic circuits by leveraging the Cadence Spectra and Lumerical INTERCONNECT. So this is also available for the Verilog-A platform, and the schematic design can drive circuit layout, and layout can be back annotated to the schematic for post-layout simulations. So we can move to the next page. And we will talk about the component design workflow first. So for the component design workflow, the designers usually see some challenges like we need to define a golden layout in both layout editors and some multiphysics solvers, which is time consuming when we try to import, export the GDS and try to fix the structure. And this also makes the problem of inconsistency between the layout editors. So most of the GDS exporting to the multiphysics tools are not supporting the parametric analysis. With the Cadence and Lumerical layout, Cadence and Lumerical component design workflow, the layout design in Cadence actually can be pixel, so the users can change some of the parameters on the layout, and is kind of like a one click to export the layout to the Lumerical multiphysics tools, and also at the same time you can choose to add the simulation region and the pores. So basically, when you add the multiphysics tools, you are good to run the simulation and get the characterization of the model. And is loading the layout to the layer builder. So you can also load in the layer information file, and also if you have a foundry process file to this process, so that the layers, the different material thickness of the component are defined, and also if there are any process variations is defined. So we can go to the next page, please. we will show a demo video of this. So this is start from the Curvy core. There is a Lumerical button here, and you can choose to export the layout to the Multiphysics tools. And you can load a layer map file, which defines the layer material and the layer thickness. And then you can choose to load a process file if you have, that is from the Foundry. So you can define some process information. And if you check the box for getting the simulation region and pores, it will automatically define for you. So when you expand it, you see the layer builder, you see the simulation region and the pores are automatically added. So since the layout is a P-cell, we can change some of the parameters of the layout. Say, for example, here I change the rotate of the layout, and we see the simulation automatically updated. So from here, you can just run the simulation and get the S parameters of the model. And we can move to the next page. And the next page. So with the S parameter ready, we can use the CML compiler to build the compact model for the S parameter with the S parameter. So CML compiler, in a long time, there is a gap between the component design and the circuit design. So the component designers will design the actual physical component and do its characterization, get the, say, for example, the S parameter, the behavior model, the behavior of the component. But the circuit designer actually cannot get the physical model of the component and usually use an analytical model or a mathematical model to represent the actual physical model, which is not very accurate. So now with the PDK development, the CML, the compact model library, can actually contain the very accurate model of the physical model to represent the physical model. So CML compiler is a streamlined tool to facilitate the process of generating the compact model library, and makes sure the models are very accurate. And CML compiler can also collaborate with Foundry, so you can include Foundry information into your model, like the fabrication variations, the process variations, and even sometimes the spatial correlation and so on. The models are very secure, so we can actually protect the model data and also the process file, so that the end user, they won't see the internal data of the model. And it's very easy to be maintained. So the maintenance is very easy, and you can just choose to update your full library, choose to update part of your library, and so on. And it's very easy to maintain. Yeah, so with the key features in mind, CML compiler is very easy to run. It has only like 3 simple steps. Oh, so this is not actually the run page, sorry. So again, yeah, this talks about the compiler with all these features, and to run it, we have only basically 3 simple steps. So the CML compiler provides tons of templates for different models, and when users try to build their own compact model library, they just need to go into the model template and update the data. So the data can come from any resources, like the experimental data, measurement data, simulation data, and so on. Once you update the data, you can run the CML compiler. The compiler will automatically compile the models for you, and it also comes with the QA test. So you can set up some criteria for the model and do the QA test to make sure it meets the expectation. And then the models are automatically packaged and distributed as well. So at the end, you will get a CML file, and you're ready to distribute it to the end users. Yeah. And so with the collaboration with Foundry partners, CML compiler can automatically load the Foundry process file. So within that, you can define the Foundry variations of the models, and also some spatial correlation, and so on. And interconnect, if you install the library into interconnect can also do the corner analysis and Monte Carlo analysis for you so that you will see the model behavior. And at the end, the CML compiler outputs the compiler model library and enables for statistical simulations. And another thing is that the CML compiler can be used to generate the interconnect models, which is which can be used in interconnect standalone and also used in the workflow we talked about today, the co-simulation workflow with Cadence Virtuoso. And it can use the same set of data to generate the Verilog-A models. So basically, you can run one scripter to generate the compiler model library for interconnect and also for Verilog-A. Yeah, we can move on to the next page. Yeah, so this is the Verilog-A models generation, and Verilog-A is like a SPICE model. It uses language for the CMLs electronic models, use the same type of language, and the Photonic Verilog-A models enables electronic-photonic co-design for integrated photonics, and it uses the same solver to resolve the photonic models and also electrical models. So it can leverage the advantage of features of the EDA simulators. So CML compiler can use the exact same data as the interconnect models to generate the Verilog-A models, and is basically just run one command line script. And the Verilog-A models also supports the statistical analysis for the corner and Monte Carlo analysis, and can be loaded in the process file from the Foundry. Now we are moving to the electronic photonic co-simulation part. So that's the bottom part of the workflow diagram we showed before. And here we use PAM4, like WDM PAM4 example to show this. So this is one of the channel of the WDM transmission line, and it's a PAM4 modulation format. If you see the black boxes here are the electrical parts of the circuit, is basically a CMOS driver, and the blue part of this is the optical transmission link. So the phase shifters, the phonome phase shifters there are just building the modulator. So later on, we will use a ring modulator as an example because it's easy to build like the max for the different channels of the WDM, and then we use our ring resonators as the Dmax for the different channels. So as always, the first step is to basically characterize the channels for the WDM circuit and do a run through of the modulator to find its best biasing point. So for this part, with the modulator, we run an like a time domain, basically a time domain simulation with a ramp source, so that is that equals to running a sweep in the frequency domain to sweep for the different bias of the modulator, and we will bias it at the 3 dB point. And this is an example of that. So we have the 4 different channels, and we can run them all together. So we use a ramp source to modulate the modulator, and you see that's the different frequency for the different channels. We use a ramp source to run the simulation as the driving signal, so that we can sweep through the different driving voltage and find the best bias point to find the best basically extinction ratio. So now the simulator is interconnect and it's running in time domain. So we use the Ultron solver, and we define the number of samples we run and also the time window. So we also set up a few of the outputs that we can view the results at the end. And when we click on run, it will generate the Photonics Netlist automatically, and also update to the running process in the output file. And you can see the results will pop up. And basically from here, we see the different channel transmission and also find the best driving point. And now is the full circuit design, so the electrical part plus the photonics part. For the electrical part, it's mainly the driver of the modulators. So we use the CMLs drivers here. And the optical part is a PAM4 modulator, and for each channel, basically. And that's the like full circuit design, the top level schematic. So you see the CMOS drivers design the electrical part and the optical part. So at the end, this is the transceiver. We also bring it back to the electrical world using photodetectors. That's the driver design. And we can expand the different parts of the circuit. So we have the transmitters. Those are the 4 ring modulators to cascade the 4 channels. And for each of the electro-optical components, we actually can define the RF electrical load model with it so that we can model the equivalent circuit and the loading effect. And at the receiver end, we have the ring resonators as the Dmax to separate the 4 channels. And we also have photodetectors to bring the optical signal back into electrical signal. And we also have amplifiers, TIAs, to smooth out the signal and amplify the signal. So the co-simulation workflow will use interconnect as the optical solver and also Spectre as the electrical solver to solve the full electro-optical circuit. And back to the ADE, you will see we use Spectre as the simulator now. But when you see the different bands of the models, you will see that when you enable the co-simulation and specify the optical settings and go to the different bindings of the models, you will see that for the optical models, it's band to interconnect as a solver. And then for the electrical model, it's band to Spectre as the solver. Okay, so we can now set up the compile model libraries that we use in interconnect directly from Cadence Virtuoso. And we can set up different output measurements so that we can plot the results. And we can generate the electrical and optical netlist. So now we can also choose to generate the unified netlist for both parts. And we can then click on run. The running process will be shown in the output file, and you will see the running like time steps. You can choose to show or hide interconnect. So here is the result we get for the 4 different channels. You can see before running through the filters and TIAs, as a receiver, the eye diagram has a lot of ripples. That's actually due to the channel crosstalk in between the 4 channels. So we can actually see at the end, the last channel signal with all the other channels filtered out, that has the biased eye without the ripples. But this can be just resolved by going through a filter. So you can smooth out the signal. Okay, so that's at the end, the signal after the TIA going through a filter and amplifier. So you can see it's a lot better with the signal ripples smooth out. And for this example, we have actually also run it through the Verilog-A platform and compare the result for the 2 platforms. So to compare, we place the TIA electrical eye diagram side by side and also measure some key figures of merit, such as the rise fall time of the eye opening. And as we can see that interconnect model results and the Verilog-A model results are very consistent, very comparable. However, interconnect models results are kind of a little bit noisier than the Verilog-A model results. One of the main reasons for this is because the interconnect photodetector models include short noise, while Verilog-A photodetector models does not include this effect. But both models actually include the thermal effect. So with more development effort, I believe we can also add this feature into the Verilog-A models. Right now, we also added a new feature to the Verilog-A platform that it can also characterize the channel crosstalk, so that we see that the interchannel crosstalk are included in both platform, and the eye opening are pretty comparable. So overall, they are basically very consistent results in the two different platforms. So user can choose the best platform for their design purposes. And just the difference is that using the interconnect co-simulation workflow, it actually runs interconnect as an engine and also Spectra as the engine as well. For the Photonic Verilog-A design workflow, all models are SPICE models, so user can just only run the Spectra as the solver. So talking about the co-simulation, it's a very powerful tool for the system optimization, and it can actually co-optimize the electrical part of the circuit and the optical part of the circuit at the same time. So usually when we do the co-design, we run the electrical part of the circuit first and import the signal to the optical part of the circuit. And we actually separately optimize the two parts and generate the results that we think is optimized. But with the co-simulation, we can actually co-optimize the two parts at the same time. And with this example, it's actually a predistalled signal that predistalled driving signal that generates the best opening eye at the end. So we can move on to the next page. Yeah, you see, so it's the predistalled electrical signal that generates the best eye diagram. We can move on to the next page. So you see a little bit difference in the eyes than in the example. That's because we plotted for PAM4 and plotted for two-level signal, like separate the levels. So just to name a few of the foundry PDKs that are available for this design workflow. So we have Tower Semiconductors PDK, and it's for the co-simulation workflow. And we are also work very closely with them to develop the Verilog-A work library as well. So AIM Photonics has the available PDK for the co-simulation workflow as well. And Compound Tech has the PDK for both platforms. So we also work with Global Foundry for the Verilog-A models that can be used in this workflow. So yeah, I think that's the end of the presentation, and I'll pass it back to Conrad.
Thank you, Guanhee, and thanks everyone for joining us here today. Just as a quick reminder, we do have this being recorded and we'll be sending it out afterwards. We do have quite a few questions as well, so feel free to stick around. We'll have a Q&A session here. And then if you're interested in moving forward with Lumerical, you can certainly contact us at RAND Simulation. Our contact information is available on this slide. Easiest way is just to go to our website, or if you have a connection with one of our account managers, feel free to reach out to them directly. Other than that, I'm going to turn it over to the Q&A section here. So, all right, so the first question we have, does interop require a license?
So the interoperability does require the licenses for different part of tools, like the Cadence tools and also INTERCONNECT, Lumerical Interconnect, but it doesn't require any Astra license. So as long as you have the Cadence tools and Lumerical tools, you can just set up the interoperability, and there is no need for Astra license.
Okay, great, perfect.
Okay.
Yep, yes, you sound good. All right, I have another question here. How do you set up the interop?
Yeah, there is a full process for the setup, and we have an online page about this. So I'll share the link in the chat window, and user can go there and see the setup process of the interoperability. Should that be okay, Conrad?
Yeah, that would be fine. Yep.
Okay.
If not, we can also, I can include this in our email that goes out afterwards as well.
Okay. Yeah, that sounds good.
Yeah, let's just do that. I will.
Yeah.
I'll put in an extra line that has the link to the Ansys Optics website for everyone to access.
Okay. Yeah. Thank you.
Sounds good. Let's see. Other question here we have. Can I generate the interconnect models and the Verilog-A models with CMLC at the same time?
Yeah, so as I mentioned before, use the same set of data can generate the models for both platform. And there is actually a command line script that can generate the two type of models at the same time. So just like deployed into different folders.
Perfect. So let's see. We have another one here. For the schematic driven workflow, is it back annotate from the layout?
So yes, it has the back annotation property. So if you use the code simulation, like the schematic driven layout simulation, at the end, you will generate the layout for the circuit. And if you make changes at the layout, it can be back annotate to the schematic design, but you will need to rerun the schematic simulation to get the results and like decide whether it's good to go with the layouts.
Perfect. We have two more here. So which model should I use? VA or interconnect compact models?
So for this, it would really depend on the user's application. And but I would say the results are very comparable and consistent in between the two platforms. The different models have their advantages, and we are actually working on a page for the comparison of the two different platforms. So after that page is published, user can go there and see the advantages of the two platforms and choose which one is the best.
Perfect. And then we have one more question here for today.
Mm-hmm.
Does the CMLC have a user interface, or is it just through command line?
So yeah, that's a very good question. And right now it's only through the command line. So it's like when you open the CML compiler, it will actually open up a prompt command line, and you will enter your command scripts there to generate and deploy the compact models. But we are actually already developed the user interface for it. So the user can actually like open up a GUI and like check the boxes, do some editing there to generate the compact models. So it's now going through the testing process. And after we make sure the GUI works well, we will like publish it with the Lumerical bundle, so the user can start to use the user interface for the CML compiler.
Oh, and it looks like we did have one more person, one last question here come in via the chat as well. Since Verilog was designed to represent electrical signals using current and voltage, is it able to represent the photonic signals accurately?
So for this, yes, that's for like an answer. And so it is a surpass model. It is designed like the current and voltage and so on. And it can also actually define the phase of the signal. And in our models, we use like multiple channels to define a single model, so that you can define it for the accurate frequency range for it, and and also it supports so that it supports multi-channel, multi-modes, and so on. Yeah, so for short answer, yes, and basically we use different technologies to make sure the model is accurate.
Perfect. All right, well, that looks like the end of all of our questions here today. We certainly appreciate everyone joining us, and especially thank you to Guanhui and Yell for doing this excellent presentation into this new and emerging technology. I hope you have the great rest of your day, and like I mentioned earlier, feel free to reach out to us via our website. That's one of the easier ways to get a hold of us, or send, if you're already connected with a account manager here with RAND Simulation, make sure you reach out to them with any additional questions you may have. All right, well, thank you everyone, and have a good rest of your Wednesday.